проверить это. Это все время доски путают.
Дело запустил.
Да, видно доски. Yeah, so on previous class we have discussed the norm map. So suppose you have prime ideal P, and so this is spectrum of A. So we have spectrum of B, and we are looking at ideals lying over our ideal pi, so you just let us record it. You have field extension. So here you have K is the fraction field of A, and here you have integer closure. Of course, this is standard setting that we shall have all the time. So we have ideal pi, and we have beta lying over pi. So if we have beta that such that intersection of it is equal to pi, and we want to calculate the norm map. So we define the norm map of beta as so you have ramification index here. Inertia index F beta, which is a beta over A mod B beta over A mod P. And we define the norm map on the ideals. Yeah, so that it is P in the power F beta. Yeah, so yes, so then we are yeah. So first of all, we have to discuss where the norm is defined. So we consider the groups and what is the origin and why we are defining it this way. So the explanation is the following commutative diagram. So first of all, we have introduced the K group. So this is a group with generators corresponding to M simple LA modules. And relations are defined the way that we say that yeah, so yeah, maybe we are defined by so the generators are arbitrary modules, yeah. So just the modules, and relations are the following. So you have M1, M and 2. So you formally say that the generator M is equal to the sum of M1 and M2. And if you consider, so in our case, yes, so you can always, yes, so if in M is finitely generated, yeah, so you can think of finitely generators, finitely generated A modules. And then you have, so here you have filtration in simple A modules. So simple means doesn't contain AC module. modules. Yeah, so here you have, of course, if you have the ring R, yeah. So any ideal is the simple submodule. But suppose it has it is torsion module. So torsion module. So any element is annihilated by some element of A. So any M is annihilated by some A. And here you have the property that if you have such property, then you can think of the following. So you can think of So if you have so if you take M and take annihilator of M, yeah. So notice that if you take the element annihilator of Bm, it will be larger. Yeah? So so for some B such that B times M is not equal to 0. So I claim that so since we have Noetherian assumption that maximal element in the chain of so consider the chain of such annihilators. So I want to prove the following, that always you have so since so here it is not clear about Artinian property, yeah? So that if we want to take just a simple submodule, yeah? So it is not a priori it is not clear that you can take M and you can take a simple submodule of M. Yeah, so for example, if you take R and because if we were working in finite dimensional representations or finite dimensional vector spaces, yes, so that Noetherian property of finite dimensionality or Noetherian property are equivalent. So usually in representation theory, the existence of simple module is evident because you just take the chain of modules, yes, so smaller and smaller submodule. If the module is not simple, you can take submodule, and the limit of this chain, the intersection of all such modules, just the last element in the chain is just the simple module, yeah? But and non-zero, yeah. So for example, in vector space, this just without any action of the group, so the smallest simple module is one-dimensional vector space, yeah. So, but here the situation is not evident because, for example, you can have a decreasing chain of ideals. And then I claim that that any so I claim that the following set is non-empty. So that we introduce the set of associated prime ideals. So that are the set of P in the spectrum. So such that there exists M inside module, such that P is precisely annihilator of this element M. In other words, if you take this M and apply A times M, yes, so A times M is a submodule of M, which is isomorphic to A modular annihilator of M, of course. Yeah? So this is now submodule of M, and what it says, so that in the case that M is taken as in the theorem, So the annihilator is P, so this is equivalent. So these are such P in spectrum, such that there exists embedding a mod P inside them. Yes, so this inclusion. And I want to prove briefly that, so what is not evident about this set, that it is not empty. So the claim is that if A is Noetherian, so even for arbitrary module M, so claim that if if A is Noetherian, then associated prime ideal, so the set is not empty. And what we do, so we take, so notice that in a more general setting, so of course, there I assume that all elements are annihilated by something, but of course zero ideal can be thought of an associated prime ideal. Yeah? So I mean, in general, so this set can consist, if you take the ring without zero divisors and take it as the module, then you get that the set of associated prime ideals is just consists of zero ideal. So which is so when we're speaking about spectrum, we do not allow the ideals equal to the whole ring there, but we allow zero ideal. Yeah. So then I claim the following, that suppose so you take annihilate of some element, some non-zero element. So this is non-zero because it at least contains zero, and take start taking the elements of the form B1 M and saying that I mean if annihilator is not the whole ring, so that you can, so is not maximal ideal. This means that you can take element outside of M. Yeah, so if it is already maximal ideal, then we're done. Yeah?
Mhm.
So otherwise, okay, everything is okay. So that means that if it is not maximal, then it will be B1 that doesn't belong to annihilator of M, and it is not unit. So that means that you will have B1 times M is not equal to 0. Yeah? So you can consider such chain of increasing elements. And I claim that, I mean, if you take maximal element of this form, yes, so that where you cannot write it as bk times m, yes, so Noetherian property says that this chain stabilizes.
Mhm.
Yes, so then if it stabilizes, then Noetherian property says that chain stabilizes, and then otherwise, so we take maximal element, so maximal element yeah, so annihilate of M tilde. If you cannot enlarge it in the way we are doing it, if we can enlarge it via algorithm. So that means we can do it and we can repeat. So otherwise, so repeat constructing chain. So otherwise we have annihilator which is maximal. So maximal among such ideals, among annihilator. Maximal among such ideals. Yeah, so formally you have to use Zhgun lemma here, yeah, because you consider the chain of these forms and of these sets, and you prove that there is a maximal element by the chain using by knowing Noetherian property. Yeah? So then you take this maximal element. I claim that it is prime ideal. So this is prime ideal. Yeah, so assume that AB belongs to annihilator of M tilde. Yeah, so and suppose also B is not an annihilator. Then you get, by previous assumption, we get that annihilator of B times tilde is larger than annihilator of M tilde. Yeah, so notice that B M tilde is not equal to 0, so this is non-trivial ideal. So that means that we have the equality. So we have equality by maximality. Yeah, but notice that note that A belongs to annihilator of B M tilde, yeah, because AB belongs to so AB M tilde is equal to 0, yeah, by previous assumption. This is just AB times M tilde, and this is equal to annihilator of M tilde. Yeah, so that means so this is contradiction. So that means that annihilate is prime. Is prime. So we prove that this. So we prove that this associated prime ideals exists, and then we can. So then we can simply do the following. So we can take M is finitely generated. Then we can filter M by A modulo T by the following algorithm. So the associated prime ideals of M is not not empty. Yes. So this means that there exists embedding A mod T inside the M. And so we can take to be this is to be the image is just M1. Yeah, so we can think of the image of this embedding as M1, and then we can pass to M modulo M one and repeat. Yes, so find inclusion of A mod pi, so which we denote by mi tilde inside m mod mi minus 1, and we denote by pi minus 1, we denote the map from m to mi minus 1, and by taking putting mi equal to the preimage of this embedding of pi minus 1 inverse of mi tilde, we get a chain of submodules that are increasing, and we get increasing chain. And with the property that m1 and 2 etc. And you have the property that mi modulo I minus 1 is isomorphic to A modulo pi, and this chain terminates by Noetherian property. So chain terminates. Yeah, so notice that so that actually yeah. So now this yeah. So this gives you the corresponding sequence of modules, and yeah, so notice even so this works even without assumption that A is Noetherian, but in the end you get a module without the set of associated primes. Yeah, so what should be noticed that as a module, so remark that if you have a module and a quotient, so that the set of associated primes of M is contained just не, я лучше ничего с этим не буду говорить. Ладно. Yeah, so in our case, we have so if when A is dedicant, yeah, so any prime ideal is maximal. And this is precisely, it tells you that A mod pi is a field. And this is precisely simple modules. Yes, so this is simple A modules. Yeah, because in any other ring, if it is not the field, you can take proper ideal. Yeah? Mm-hmm. So that's why it is not simple. So in any other other case is that you can take I mean, so you take, so if you are thinking about simple module, it should be generated by one element. Yeah? So such submodule is isomorphic to A mod I, so A mod annihilator of M, and if annihilator is not maximal, then this, when annihilator is not maximal, so this is a ring, of course, in commutative setting. So the ring A mod annihilator of M contains non-trivial ideal. And this is precisely the submodule, and that's why this is if and only if. Yeah? So so this is description actually of simple ideals, and this means that you have filtration by simple modules in our case. So this proves that if any element is torsion, yes, so that that means that you can have this kind of chain, and in this chain pi are not equal to 0. Yeah, because this means that in our chain pi's are not equal to 0, and this means that we get filtration by simple modules. And now, so this means that generators of K group in this setting, yes, so for torsion modules, is precisely the A mod P. Yeah?
Yeah, but what about not torsion parts, like free parts? Why they are not contained in KFA?
Yeah, в смысле, они so they are contained, but I'm speaking about the subset of K.
Okay.
Yes, so.
Yeah, that's
Yeah, it just it is the remark. Yes. Yeah. So if you want to speak about yeah, so here we have the extensions of rings. Yeah, I just wanted to explain how we construct this filtration. I mean, in arbitrary setting, but of course, I mean, here in our case, the situation is also simpler because if you take the ideal, yeah, so you shall see it, yes. In a sense. So if so now you can take the two rings that, and we can have so we have the maps between K groups. Yes, so actually in two directions. Yes, so if given a module, B module, yes, so you can have the map to KFA, which is a restriction. So you can say that it is restriction from A into B. Yes, so I'm saying that this is considering M module as A module. Yes, so this would consider M as A module. And you have an inverse map. Yeah, but you can take N to be A module. And you easily construct the B module by considering B times A over N. Yeah, so this is now B module. So you have maps in two directions, but we shall need actually restriction. I mean, one can think about more non-trivial map, but we will be interested in restriction. And notice that so here you have a nature. Yeah, so also you have a natural map to ideal group. So this is ideal group. A group of fractional ideals. So group of notice that it is not the class group where you factorize by additional relation. So group of fractional. And actually we introduce fractional ideals in order to make the set of ideals out of the set of ideals of the group. Yes, so you can always multiply them, but when you introduce fractional ideals, then inverses appear and you just work it as with group. And this is done as follows. So you're out of the module. So the module, so you have to associate ideal. So we associate ideal in a way that R, the ring A, the ring B maps to 0. Yes, so we introduce this map. So such that B maps to trivial ideal. Yes, so I mean B maps to B, but B is a trivial element here. Yeah. So this is the class is a unit element. So this means that you can think, so if you want to have an arbitrary module, then you take minimal, so you can take a presentation of yeah, so you want to, you can think of yeah, so this is finally generated module. And you do the following. So if you take, but let us assume that it is torsion module. Yeah, so we can assume that M is torsion. But by the following observation, so if you have, I mean that by the following, so assume, so if it is not torsion, then you have inclusion of B into M. So assume that M is not torsion, then there exists inclusion of B into M, and we can pass pass to exact sequence B M modulo B, and this yes, maybe I shall write like this. I of B, the image. Yeah, so this so we can pass to this quotient,
Yeah, that's true.
and In K-theory, of course, so this is, you will have the relation, but from the viewpoint of the image of this map, so this is called chi of B. So the image will be the same. So
Is chi of B a group homomorphism?
it's a group.
Uh-huh. Yeah, but
We define it as a group homomorphism.
yeah, okay, I understand. But isn't in K of A unit element is 0?
Yes.
And where 0 is going? Shouldn't it be going to unit element, so to B, but it's kind of strange.
Just a second. Да, давайте это потом отключим. So M just M is just equal to M plus M modulo B plus M modulo image of B. So we can assume that we work with the torsion modules. We work with torsion modules where we have the filtration. We have filtration. Тут как бы нет ничего плохого, на самом деле, в том, что вы сказали, потому что это же не гоморфизм коллекции, это гоморфизм группы.
Да,
Поэтому аддитивная группа, но она может отправляться, нетривиальный элемент может в ноль отправляться.
Так мы же К от А рассматриваем только как аддитивную группу. Или кольцо?
К от кольцо, в принципе, относительно тензорного произведения. Но здесь мы, в ней ноль отправляется в тривиальный элемент, а любой другой может тоже в тривиальный отправиться. В частности, мы бы отправляем в тривиальный.
Просто мы К от А как группу рассматриваем относительно чего?
Сложение.
Относительно
В смысле, точно по одной последовательности.
Да. И 0 мы там отправляем в Б.
0 отправляем в Б, но и Б отправляем в 0. Ничего плохого.
То есть мы как бы оставим такое кручение.
Все
свободно,
so we can work with only the torsion modules where we have filtration, and we just map additive group to multiplicative group, but we do not take into account that K could have the ring structure, so 0 is just a unit element maps to unit element inside the ideal group, and the ring B also maps to trivial element. And when we work with torsion elements, this means that you can consider this filtration, and using this filtration we map. So if we consider this filtration, modulo mi, where mi minus 1 are isomorphic to A mod pi. So we map M is mapped to the product of the corresponding pi's that appear in this decomposition. So notice that it is convenient to map it in this way, I think. So then we think of the following. So we stop at so we stop here at MN. I mean, when we're writing down this product, of course, I mean that PI's can be equal to each other. Yeah? So just PI's can be not distant. Yeah, so this allows us to write down the group homomorphism, and notice that note that why we introduce the norm, so that in order to make this I claim that the norm is introduced in terms in order to make this diagram commutative. So norm of ideals, norm on ideals is introduced in order to make diagram commutative. And via via restriction, yes, so there is a map that is restriction, and you have so here you have chi E, here you have chi A, and here you have this norm map. So notice that yes, and this is chi of B, and the reason is just that if you I mean how we are introducing so. Yeah. Also, you have the following. Also, you have the following. Important. The following important property that if you have an element of B, yeah. So given. Given given psi, the element of B, yeah. So you can introduce, and this norm, as we said, it is defined on beta in order to have it. So this is here in this index, and notice that this is precisely the following. So if you take how we can calculate this kind of formula? Yes. So how we have obtained this formula? Yes. So we should работает. Ладно.
А можете назад, мне кажется.
Я ластик взял.
Да. А можете назад нажать, если
Да нет, я тут хочу переписать. Yeah, so we define norm of beta. So by this formula, now it is clear why we are defining it. Because if we consider instead of beta, we can consider A mod beta. Yeah? So we consider A mod beta, извините, B mod beta. Yeah? So we considered B mod beta as a module. Yeah, so the restriction is considering it as a module. So of course, yes, I'll notice that. Yeah, so you can consider beta, of course, as a module, but it is not convenient because it is too big. I mean, it is ideal, so it is not clear how you decompose it. But if you can see that, so noticing that B maps to 0, so we can consider B mod B as a module. Yeah, so we get the which is a restriction. Yeah, so map. So this has so actually so this guys has not the same images, but they are inverse in the group. Yeah, so this the inverse classes. So so the class beta is equal to so maybe so here in ideals you are saying about multiplicative group. So we have this kind of equality, but if you consider this as a module, it is equal to a mod P module. As since P is since P is precisely the intersection of beta with A, yeah? So and it maps to 0 when you multiply element of beta mod B, and this implies that so of course beta is not A mod P module, but this quotient is A mod P module. And then since A mod P is a vector space now, so A mod P is a field. So B mod beta is the A mod P as A modules. It is A mod P in the power F beta. Yeah? So this is a sum of the corresponding copies. Yeah? So this means that you just associate thinking of it as the restriction. So the chi of A of the restriction of B mod A on B mod beta, it is just chi of A applied to A mod P in F beta. So you use multiplicativity, and this is pi in pi inverse, yeah, in F mod beta. Yeah? So by multiplicativity and the rule of taking sides, yeah, so they are inverse to each other. So so the class A.
So how we define chi A? We define that A mod P goes to pi minus 1, or
we define that A maps to 0.
A maps to 0.
A maps to 0.
A maps to A.
A maps to unitel. Yeah, A maps to A, so, well, A maps to unitel.
Yeah, and A modulo P maps where?
Yeah, A modulo P, of course, by this rule, because we have exact sequence. Yeah, it maps to the inverse of.
Yeah, that's what.
Yeah. So, so that means that. Yeah, so that they. So this is a class of A. So this maps to unit. So this is multiplicativity of the sum maps to, so the sum of classes. So the sum of I. So the sum of modules f times maps to. Let's see. And this so these are inverse. Yes. So chi of E is equal to inverse of chi of A. So this explains why we have to change it. Yeah. So and this shows that our definition is quite natural. Yeah. So not only due to the formula that we have discussed about restrictions and yeah. So notice that if you take if you start with pi, yeah. So remark about multiplicativity formula that we have obtained. So the formula that of the form that k, so the degree, yeah, so the formula for the following situation that if you take pi inside A, and if you write PB in as beta 1, E1, etc., beta n, En, yes, so you can obtain the formula of restriction and so you can obtain this as this is induction, and so this can be viewed as induction and restriction. Yes, so that means that inside B, where you do not have zero divisors, yes, so that P tensor A B inclusion is. So it maps to P beta inside B. Yeah, so since B has no zero divisors. So the formula can be viewed as induction and restriction. So this formula, thinking of considering as A modules, so considering it as A modules, so you can think of this as considering induction. Yes, so taking tensor product and then restriction of E and restriction. Yeah, so taking tensor product is just it is called induction sometimes, because it allows you to think of A module as B module, and this is so if you apply this formula, then notice that. So in order, notice that the A mod, so when E is factorial, yes, unique factorization domain. So any idealist principle. Yes, so No, principal ideal bankrupt, sorry. Yeah, so you see that we have noticed that beta is just the nth power of A. So beta is isomorphic to A to the power n. And this implies that A mod, B mod P beta, it is just isomorphic to A mod n modulo P A mod n, so which is just A mod P to the power n. So you see that induction and restriction is multiplication by n. In this case. And if you do it, if you apply this character, then if you apply KFA, so you will notice that this is also multiplication by A. Yeah, so if you apply KFA to restriction and induction, yeah, so you shall get the application of norm. So taking restriction, it is equivalent to application of norm to beta 1 E1. Yeah, so I can write it down by multiplicativity. And this is not surprising that we get this is P inside the F1 E1 times etc. P Fn E. So the so which is P in the power n. Yeah, so this is also multiplication by n.
Yeah.
Yeah, so from the viewpoint of taking pi. Yeah. So this is called transfer sometimes. So transfer map.
Yeah, and the last one, when we consider chi of A, this works everywhere, not only in PID.
It was.
When we say chi of
Yeah.
This,
Yeah. So of course, I mean, this is just interpretation, and but yeah. So the problem that this is not global property. Yeah, so it is up to I would say that so from geometric point of view, so this the things where you have this kind of decomposition, it is devices. Yeah, so because when you so the Dedekind property is precisely a thing that any prime is maximal, but when you localize, so there could be many ideals that exist. So P, when you localize by P, it becomes not. The ideals that lie in your P before localization, all prime ideals that lie in P, they survive.
yes.
So if you are thinking about geometric so Dedekind property precisely says that there are any prime is maximal, so there are no prime ideals after localization.
Yes.
So that means that your prime is the smallest ideal,
Yeah.
and that means that it is codimension 1 ideal. So that means that this, but notice that you cannot obtain the formula. So when you of course localize by principal ideal, then you get of course yeah. So if you localize in the normal ring by ideal of codimension 1, you get discrete relation ring. But this formula becomes a little bit stupid because there will be only one factor in this formula. But what it really means is that this formula is valid up to, this formula first of all can be checked by calculating right and left hand side via localizations. So such multiplicative formula can be checked by localizations. And so this formula works up to codimension 2 ideal.
Okay.
So, which is not surprising. Yeah? So,
Yeah, you wanted to say about transfer map.
yeah. So, this is called transfer map. I mean, you have two maps in two directions, and their composition is just multiplication by them. So there is usually evident map and not evident. Yeah, so here the pullback, so the induction here is evident map. From geometry there are two maps, push forward and pullback. And usually, if you have F, yeah, so if you have shift here and shift here, so you have a pullback map of G. Yeah, so that usually exists, and it preserves the properties of the, for example, of finiteness map. This means, but as for push forwards, sometimes the push forwards do not have the properties that, in some class of modules, push forwards do not. So, for example, you can take coherent sheaf, so that comes from finite dimensional modules, finitely generated modules, and when you apply push forward, the sheaf doesn't preserve this property. Yeah, so if you take even finitely generated module, so for example, the example is very easy here, so you can take K that belongs to K of T, yeah, so the subset, you can consider K of T itself as a module over itself, which is finitely generated, but over K of T it is not finitely generated. So this means that the property, this operation has a restriction from A into B, and which is precisely the analog of push forward in algebraic geometry. Yes. So it can just throw you out of the category you are working in, and that's why when this is well-defined map, you call it transfer in this direction.
Okay.
For example, when this map has compact fibers or proper maps or something like that. But for those who haven't heard of this, that is not important. So so this is about. And now I want to say why this norm also is. Also we have the formula. So if you have eta the element of the ring D. Yeah, so it is we can define norm of eta. Yeah, so by the formula using the norm that we have used, I mean the ideal norm. Yeah, so the norm of so you can generate the principal ideal. So to the element we associate principal ideal, and we associate this norm. And also you can do it in the other way. Yes, so we consider it as a multiplication. So standard way. So we can consider a multiplication by A. By psi on on the field L. So this is a map from L into L. And we can take a determinant. So this is linear operator. Linear operator where you can take determinant. Where we can take and the claim is that this means that so after multiplication, after considering determinant, yeah, so this is a number, but you may think that this is ideal generated by the corresponding number. So the claim is that n of psi, if you take n of psi and generate the ideal, principal ideal in A. It is equal to n of psi defined this way. So the two definitions of norms are consistent. So the two definitions of norms on elements are consistent. So this means yeah, so let us check it. Yeah, so so again we reduce it to the calculation that we can by let me say about the proof. Yeah, so by the exact sequence, so we're so we reduce calculation to the quotient. To calculation of restriction of B modulo of psi beta, so from B into A. And when you think of this, so this is just notice that this is in order to calculate it, so you take it as a module, And you have to consider filtration of by principal ideals, not by principal, by prime ideals, so filtration with pieces A mod with factors A mod pi, and then you take a product of a prime ideal. Yeah, so I recall how we are calculating it, yeah? But, how we are calculating determinant, yeah? So in order to calculate the determinant, so now, when you are taking this product, so I claim that they are all maximal. So if you take this filtration and localize it, so only so this is the remark. Remark. So since PIs are all maximal, so you have to when you're thinking about this filtration, you have to take into account the multiplicity of the factors, yeah? So multiplicity of the factors, how many times the factor appear, yeah? So if you take this filtration, so the multiplicity, since they are not all primes are maximal, so they are maximal and minimal at the same time. They do not contain each other. Yes, so that you can do the following. So you can localize this. Calculation of multiplicity of the given pi. Is reduced, well, PG, so I mean different context, yeah, of the given P. Yeah, so it reduces to taking localization. Yeah, so you can use the same filtration, but when you take the localization, the factors where the differ, so we can take, calculation of multiplicity can be read of filtration, where all modules are localized by P. So note that if you take, note that if you have the property that mi modular mi plus 1 is a mod q, yes, so that means that simply this means that if you multiply by q mi, it is equal to mi plus 1. Yeah, so it will be the subset of mi plus 1. But notice, yeah, so we have inclusion. But after you localize, if if q is not inside the p, so that means that so there exists an element q that lies in A without p in the multiplicative set. So after localization, it is invertible. So after localization. It becomes invertible. And this means that they're just equal. Yeah, so this means that if you can map it, so if you take so this Q and times M1, and this is a subset of Mi plus 1, yeah, so, and you have the converse containment, so this implies that Mi in the localization is equal to Mi plus 1 after localization. So this means that you have the same filtration, but sometimes, and nothing happens with the pieces that comes with localization by P similarly, and so you get rid of multiplicity via the given filtration, but after localization. So so after localization. But yeah, so here, of course, so what we use that you are just you do not have the factors that are embedded. Yes, so that I mean the factors that can affect this localization are precisely the factors Q that really sits inside P. Yeah?
Yeah.
So they are called sometimes embedded components in algebraic geometry, or embedded primes in associated prime decomposition. But here we do not have.
Yeah, but we don't
Yeah. In our case, in Dedekind rings, we do not have. So then, just I simply can say that we can check. So if you want to check the equality, so checking the equality of this form, so checking it in Dedekind rings. Yeah, so so you take norm of element and yeah, so yeah, maybe I should say something about ideals. So checking equality of the ideal I is equal to Ga is equivalent to check it after localization. For all localizations. For any pi. So this means that we can just localize in order to so we can prove it the equality of the norms after localization, and after this it will follow that since how we calculate, so since in order to check the equality on ideals you can localize, and checking so the in K theory also it is consistent with localization, so we can so we can just check equality after localization. Okay, after localization. By P. And here the situation is as so it is the best as possible. So because after localization, just B becomes so A is discrete relation ring. Relation ring. So that means that A is principal ideal domain. So we use the following. So we use that B is just A to the power n, and this means that psi times. So we consider the module psi times B. It is just psi times an. It is also free module. And so also free module of the same rank. And you can write it down as in the basis. Yes, so thinking as you can think of n and m. So this is free module an. So this is so here you have generators, and you can write down the generators in terms of the coordinates of an. Yes, so generators n1 and here the set of generators is the same as the number n here. Yes, so you're writing down n1 mn. So you're writing down it in terms of matrix, and the claim about principal ideal domain that you can change basis here. No basis. And you can change basis here. So in an. So writing down this. So also by changing of basis. So here this means that if you write down the elements in the matrix, you can add the rows and add columns. Yes, so changing basis in an corresponding to change of rows by adding two rows and to each other and just some interchanging them and subtracting one with coefficient which is an element from A. And changing the columns corresponding to M1, Mn, and saying that the modulus, this change of basis will result into that this matrix can be diagonalized. Yeah? So. So the theorem on about the structure of submodules over principal ideals domain says that after the change of basis, yes, so this matrix can be diagonalized. So the submodule is actually the product or the sum of the standard copies D1 A1, so D1A plus D2A, etc. So and this when you take quotient, of course, this is yeah. So of course there is also some kind of divisibility property about this fact. This is a result of the algorithm. Yeah, so actually, so D1 is less divisible, so D2 is divisible by D1, so DI is divisible by DI minus 1. Yeah. So these numbers increase during this procedure. Yeah, because. So this means that if you take a modular n, Yeah, so as the module, which is here by B modulo psi b. It is just a d1a plus etc. plus a dna. And this means that this element maps, if you apply chi to b modulo psi b. Yeah, so chi a, yeah, so meaning that you are taking restriction. It is a product of this corresponding chi's. And this is precisely the product of the corresponding D1 as the ideals. Yeah?
Yes.
But this is just the determinant of the matrix, yeah? Which is equal to determinant of matrix.
So isn't it should be with -1?
Yeah, I mean, so here, yeah, so I shall. Yeah, so I mean, I shall write down like this. So determinant of multiplication by xi. So because this is determinant of the matrix where that we are considering. Yeah, so that's why. So this is a not so trivial observation. Of course, yeah, but I would say this is most general way to put it, because the standard now the corollary, yeah, so that corollary here is the following. Yeah, so corollary when A is equal to Z. Yeah. So when A is equal to Z, or the finite field, yes, so when the quotients are finite, then you also can do the following. So if you take I as a non-trivial ideal, so A mod I is a finite abelian group. Yeah, so this is finitely generated group over Z, and if you are thinking of ideal, so this you just notice that this so notice that if you have ideal, then you can always have the following. So if you have ideal, you can always take the element from the ideal, and you can. So ideal is bounded by A and D. So this is from this point of view, there is a surjective map from ideal. Just so note that I is finite abelian group. Say for the following reasons. So if you take D inside I, you have this kind of map. So we have the surjective map A mod dA is a surjective map to A mod I. So this is surjective map. And from the viewpoint of Z, yeah, so also, yeah, so notice that the intersection with Z is not trivial as well, yeah. So we have assumed that, yeah, so not the A is equal to Z.
Yeah, just algebraic integers.
Yeah, I meant is algebraic integers, algebraic integers over Z. So you can take D it belongs to I intersection with D, which is not zero. Yes, so we have proved that this is not zero, by considering just taking any integer element from I and taking the last coefficients of integer equations. Yeah? So we have this surjective map, and from the viewpoint of Z, this is just Z to the power n modulo D, Z to the power n. So A is isomorphic to Z to the power n. And so you have surjective map from the abelian group to this one, and this is finite abelian group. So more generally, so this is torsion module. So this is always torsion module for, but this is also a torsion module for Z. So this means that you have this kind of property, and you can think of one can introduce norm. So one can introduce further maps. Yeah, so that you can consider chi of A, introduce this map to chi of B, and here you can introduce the map to Z. Yeah, so which is so to ideal, it associates the number of elements in this ideal, and notice that if you think about fractional ideals, yeah, so if you take so the fractional ideal is the product of ordinary ideals. So this is just a well-defined number. However, you can think of and this norm is just what is said here. So this norm is consistent actually with this product. I mean, if you think of this diagram, yeah, so here you have so here you have maps to Z, so these are I mean, if you consider norm map, then this is commutative diagram. So this is commutative. Yeah, because it is more or less, this does, for very trivial reason, because, I mean, you can think of not as the maps from I of B to Z, but from the maps from K group to Z. Mm-hmm. And if you are thinking about K group to Z, so this map doesn't depend on if you are taking A module or B module. So it is just the number of elements in the quotient.
Yeah, but it's number of elements in A modulo I or in B modulo I.
I mean, so here it is just a number of. So this is for I, but for finite modules it is just the sum of. If you have finite abelian groups already here, so it is just the number of elements. So both and so the reason is that this diagram is commutative. Is commutative. for finite modules and for finite abelian groups, finite modules that are finite abelian groups. Abelian groups. The composition is just the sum of elements. So the number of elements. So this diagram doesn't depend on so this compute with restriction. With restriction. So this shows that maybe, well, at least from my point of view, this is most conceptual way to understand this. Yes, so that you have some kind of calculation. That it is just for the module we associate the number of elements, but then you should think about. I mean, there are two options: either to so the problem is that in of original, I mean, of definition of norm, that if you define it by the formula, it is completely non-trivial. That this is well-defined map. And either you have to think of that, to take into account that you are interested in the number of elements and you match it. Mm-hmm. But matching with maybe better to match it in this commutative diagram, where the norm map, where here in a commutative diagram, the map is a rather evident map, and you do not define this n by ad hoc formula, but you calculate the formula as we have done it, and then we understand that the consistency with the number of elements, which is evident because the restriction is just the map that doesn't fill this kind of, I mean, taking the number of elements doesn't fill the way you pass the restriction. But so why it is most natural? Because otherwise you have to check something about the application of norm in this formula. That's why it is not so. However, you can see that in order to check it, you have to do all the things that so you should have to find this filtration and key theory, and so that's why it is. So the consistency of this formula is just. I mean, it is a reflection of this kind of theory. So just. But given that it is more, it becomes more conceptual. So let us do a short break. Yeah.
Okay. And, I have a question.
Yeah.
Like, so if we have some ideal in B, this map just counts elements in B modulo I.
Yeah. So that is a slight problem. Yes, so this map is not thinking of the number of elements. I mean, however, you have to should put -1 sign.
Yeah, so it should
yeah, but
it should count. Yeah, it's minus.
Yeah, but yeah. So that is the problem is that this map is. I mean, why this map is well defined? It is defined on commeasurable sets. Yes, so that means that if you so you do not have an absolute number for your module. You have to compare your module with something. Yes, so that means that if you have two modules, M and N, so you have to do the following. So that they are both submodules somewhere, so like in M tilde. And the idea is that you can find submodule here, find submodule here, like P common submodule, so such that M modulo P and N modulo P are modules of the type of the character, so they're modules where we can calculate the characteristics, so like the number of elements. Yeah, so they are modules where we can calculate some number, some characteristics, some function, so for a function, for example, lambda. Yeah, so and you can, if it is additive, yeah, so if you know that lambda of M1 plus lambda of M2, so it is additive lambda, and for the modules of the good form, like so they that belong to your category, then you can compare. So you can say that chi of M, so you can associate the function to chi of M by knowing chi of N, yeah? So chi of N, just, it is calculated like chi of MP plus chi of P. Yeah, so chi of lambda. I said lambda. Then put chi. So lambda of M can be calculated as lambda plus lambda of P. Lambda of N can be calculated like lambda of N mod P plus lambda of P, and even if lambda of P itself is not defined, yeah, so you can cancel out and define like a lambda of M minus lambda of N is equal to lambda of M P minus lambda of NP. So we're saying that we define it like this, yeah, so define it by this formula, by the formula, and that means that we're not defining it absolutely by the modules, but we're defining it by the difference, by knowing the difference. Yeah, so so this and this can be very, so this is a general, rather general way of argument. So I mean, if you have attended so there were lectures a few months ago about Cantu-Carrera symbol, and that was the idea about taking the term. So if you have, for example, infinite vector spaces, so you can also try to, or a class of such spaces, infinite subspaces. So you can define something like determinant or like relative determinant for or relative trace by considering these differences. Yeah, by considering the common subspace, common invariant subspace, and I mean, of course, this has to be explained, but then you can. introduce, for example, if you have the space with the big space with the operator, however it is infinite dimensional. So for the subspaces, you can introduce determinant by this consistency. So, I mean, it will be relative. And this is a rather general construction, and also it can be seen here. So maybe let's do the break. интересно, что ну, вот это вот, как бы, доказательство, но оно как бы в книжках по теории чисел, оно закопано, ну, то есть, как бы, и вот, ну, самая явная форма, это вот в серии написано, то есть local fields, ну, там, core local. Ну, как бы вот, ну, когда я это там увидел, все-таки это, конечно, самое лучшее вот, чем просто проверять какие-то миллион формул.
Не, ну а мы же по итогу, в принципе, более-менее проверили основную форму, то, что норма, ну, с нормой там коммутирует, и то, что норма действует так же, как ту норму, которую мы определяли. А там еще, да, дофига сейчас всего будет, да, что надо проверять, или...
Не, ну, тут как бы, не, ну, просто больше-то особо нечего.
Ну да, ну просто мы же, получается, не определили, в принципе, вот так это...
Не, ну, я имею в виду, что, как бы, ну, что такие, как бы, проверять формулы без какого-то, ну, общего, ну,
понимание, что это
да,
вообще такое.
да, что это вообще такое, зачем это делать, ну, как-то мне морально тяжело, поэтому.
Ну да, правда. Пока что, да, непонятно.
И на самом деле, вот как бы в этих тоже вещах, ну, как бы хорошо иметь самое общее всегда определение тоже, ну, вот, как бы, какие-то вот именно про... Ну, очень часто, вот мы тоже поговорим о дискриминанте, вот, ну, как бы увидим, что отображения, они определены в более общем контексте, а вот конкретная формула верна, ну, поскольку, но при этом, ну, как бы, вот, в некоторых книжках там, как бы, сразу проверяется формула, а в некоторых, ну, как бы, все-таки обсуждается вот это более общее отображение. Ну, это как формула для дискримината, потому что формул много, а что это за понятие, все равно там как бы требуется некоторых усилий. Ну вот как бы мы об этом тоже поговорим. So now I want to pass to the following topic, which is so this is really why I was recalling this formula. So this is the class group and its findings. Class. And actually, so from I do not quite sure about why people started discussing Dirichlet principle and pigeonhole principle and call it at least in some literature Dirichlet principle. But this is precisely the theorem by Dirichlet. Well, actually, there is a theorem on units which is proved more or less similarly. So, and this is precisely the theorem of Dirichlet, where we shall use Dirichlet principle. And maybe, I'm not sure about this, but maybe it is why people started calling it Dirichlet principle. And so, but maybe this is misleading. Yeah. So, I mean, maybe he just liked this principle so much that he stated it and then started using it. But I feel that some people just start schooling something by name, not for in way. I mean, not for in way, because the principle is quite easy. I mean, I'm sure that many people has used it before. So then, when you have finite extension, finite field extension, so here. Here it is important. So far it wasn't such important. There wasn't. It wasn't such important that we worked over algebraic, so over Z. But here it will be important that we work over algebraic integers. So you have Z here, and you have now O, which is integral closure. So I denote it to emphasize that it is integer closure of Z. Yes, so here we define, so we discuss fractional ideals. Yeah, so which are, so we can use it, so this are okay either by finitely generated okay submodules, yeah, so or equivalently there exists C, so such that C times A sits in OK, so this is ordinary ideal. So now we can recall that, yeah, so so as we have learned that OK sits inside 1 over D omega 1, etc. Yeah, so the Z omega 1 plus Z omega n, where you can take them as the subset, and actually, so since Z is, so this is a submodule of a free module, so where omega I are integer, and we have proved this, yeah, and Z is principal ideal domain. I am just recalling, just not because you have forgotten the previous lecture, but because it is like a new set of notations. So I just want to say that now OK is a free module, is a submodule of a free module. Of a free module. So of K also contains Z omega 1 plus Z omega n. So integer elements, and they are basis of L over Q, of K over Q. And yeah, so OK is a module of a free module. Then OK is free. Yeah? So we can. So OK is just a lattice, and it is generated. So all elements are written in terms of corresponding linear combinations. And yeah, so this is just to fix the notation. It's not something new for you. And also we introduce class group. Yeah, so class group of OK. So this the group measures how far the ideal is from principal ideal. So we say that A is equivalent to B. So if there exists C in K, so such that so so we take fractional ideals, and so such that A is equal to C times B. So you see that this is so the fractional ideal is equivalent to the usual ideal via this equivalence relation just by definition. Yeah? So thinking of the class group, you can start so at least you know that generators of the class group are of course all prime ideals, but I mean you may think of you can just yeah. So the claim is so the theorem that we're going to discuss that in this case the class group is a finite group. So yeah. So notice that just yeah. So as so for ideal inside of K, we introduce the norm of ideal as before, yeah, by the checking the number of elements. So we have noticed that it is finite group, so we can introduce the number of elements in this. So this is finite group, and yeah. So notice that. That we have the following formula for norm. I mean, we have this kind of formula for norm, and we have two observations that if we introduce the norm as norm of the element as multiplication, as the determinant of multiplication. So
shouldn't there be somewhere minus? Norm of A is minus.
Нет, ну вот тут как раз тут лучше, ну, ну в смысле вы имеете в виду в минус первый. Нет, ну как бы.
Скорее именно минус, там же по сумме они в z, ну это же элемент z как бы. Мне кажется, как будто должно быть минус, чтобы там совпадало с коммутативной диаграммой.
Нет, ну нет, просто как бы там, когда вы отображаетесь в z, вот там надо перекинуть, ну, там нужно, чтобы норма от А была. Ну, как бы у вас есть отображение в группу идеалов, вот, там не важно, где вы в той диаграмме ставите минус перед самым концом.
Ну то есть вы просто, в смысле, это норма, это мы отображаемся как бы в...
Ну, мы давайте вот здесь ее введем вот так, да, ну, то есть как бы просто, ну, с вабелевой группой вы всегда, конечно, можете композицию собрать, да,
конечно.
Вот, поэтому, ну, и как бы это вопрос, где вы поставите знак в коммутативной диаграмме, ну, вот перед самым концом z или, ну, давайте вот так.
Okay.
То есть, ну, чтобы для элементов, как бы, она была тем же самым. Yeah, so this is so determinant of multiplication by psi from k into k. And also notice that since, so what we know about this formula, that if you take so the norm of, so the norm of k over q of psi. Yeah, so we had a formula that defines this as a product of all the inclusions, sigma psi, all possible inclusions of sigma of k into algebraic closure of k. Yeah? So this yeah, so also you will recall that since z is integrally closed, yeah, so if you have the situation about the field extensions, yes, so that may recall that if you have the norm which is defined for the extensions like this, yeah. If A is algebraically closed, if integrally closed, and B is integer over A, so the norm of B sits inside it. So we have discussed it about the trace, but this is also true for all, actually for all possible symmetric polynomials with respect to the roots. But why people use only trace and norm? Because these are polynomials that are most easy to control, because norm is multiplicative and trace is additive. So people do not use other polynomials usually. So this, yeah, and of course, yes, we know. So this means that in our case, the norm of k over q, it is really the integer number, and this is equal to the norm of the corresponding ideal. So which is convenient because you can calculate the norm via the L. If you have principal ideal, you can calculate the norm via the element or in other terms. So notice that if then if you have an arbitrary ideal, yeah, so you can decompose it into arbitrary ideal. How we're going to prove the theorem? So that class group is finite. Yeah. So why class of OK should be finite? So this means that given arbitrary ideal, so we have to find representative of, we'll find representative from the finite set. Of class from the finite set. And I claim that the set will be defined as follows. So which is so I claim that bounding the norm is enough to define the set. So the norm of A less or equal than C for some. So why this is enough? Yeah, because it is not clear from a priori. Yeah, so because this means that how we can study behavior of the norm of arbitrary ideal. So let us decompose A into the product of primes. And now I claim that the bound, the bound, this bound will give you the bound of the integers that appear here and the bound for pk. Yes, so notice that the n of A is just the product of norms of pi's and i's. Yes, so notice the following, that if you have pi's, so pi's are now elements of A, so that they are prime ideals. But each pi lie over P, which is obtained by intersection of P Z with pi's. And notice that if, so what we know about this pi's, so for each P, we know that there are only finite number of primes lying over it. So there exists finite number of primes.
Isn't there like only one that lies over? Yeah,
No,
so
lying
lies
over. Yes, so
there,
you have P. So you have something that we do not. So we want to control A. And so we just so you have some pi's lying over P, and actually A is obtained by taking different p's lying over different primes. But you know that at least for a fixed P, there is finite number of primes lying over it. So I claim that first of all, yeah, so if you bound norm, yeah, so if you bound norm, this means that yeah, so you can write explicitly this function. Yeah, so of course, so here I'm writing the formula. Just for simplicity. So what we have to use is yeah, so let me write it down. So you are writing down this this is just since pi I is lying over pi, then you are just taking the norm of so p in the power pi I, and so this bounds C. So what you have to know about this, that the norm of each pi I is integer number. Yeah, so it is corresponding to this pi in the Fi. And if you fix this integer number, so there are only a finite number of pi's that can map into this integer number. Yeah, so this bound C gives you, so since you have this inequality, this implies that P is bounded, of course. Yeah? and ni are bounded. So the powers ni are also bounded. So P is bounded. So you see that the corresponding prime numbers are bounded and ni are bounded. There is only a finite number of bounded prime numbers here, bounded integer numbers. And for each prime, there is only a finite number of PIs possible. Yeah, so this means that we have finite number of possibilities.
Yeah, but we should say something like if we have two elements equivalent in class group, then there's norm equivalent.
Нет, мы просто нет, мы говорим, нет, я же не доказал теорему. Я просто сказал, что число элементов ограниченной нормы конечно.
Да.
Вот. Ну, как бы, вот, больше ничего. Okay. Но, чтобы доказать теорему, я должен показать, что что у меня есть большая константа, которая зависит от поля, такая, что для любого элемента из группы классов найдется эквивалентная ему маленькой нормы. Конечно, если вы любой элемент из группы классов умножите на большое, даже целое число формально, да, то есть как бы идеал-то будет формально тот же, но как бы, ну, вы можете выйти за предел идеала, взяв что-нибудь, ну, то есть как бы относительно z-модулей, да, вы можете уйти за счет как бы дробей, да, числителей и знаменателей. То есть поделив на любое целое число, но при этом еще и умножая на что-то, вы можете
выйти. Понятно. То есть мы просто пока.
Yeah, so you have finite number of possibilities то есть мы как бы не используем норму как на группе классов. Да? Ну, в смысле, она зависит, конечно, от группы классов. Вот, so you have the finite number of possibilities for ideals pi I and their powers. So so finite number of n, finite number of e's. So now we will be searching for the set, yeah, so that then for any ideal. So we shall so usual ideal. So now we do not care about fractional ideals. We do care about usual ideals. So to each ideal you associate, we shall associate usual. Yeah. So notice that about the fractional ideals, since the norm can be a fraction number, so this doesn't have meaning. I mean, the boundedness doesn't have meaning. So we introduce the group of classes. We work with fractional ideals because we want to have inverses. But if we want to speak about generators should be taken from the integer set, like integer numbers in Q. So if you are speaking about so to each ideal, we shall associate ideal with the property that norm of B will be less or equal than constant. Yeah, so actually in the class group, B will be equal to A inverse in the class group. So we will search not for equivalent element in the class group, but it will be inverse of equivalent.
Yeah, but in class group A inverse and A is also equivalent. So,
Нет, почему?
ну, потому что там можно на любой, ну,
Нет, бро, это
да.
А минус первая, они обратные.
Да.
Но как бы но не эквивалент.
Да, правда.
И заметьте, норма, да, если у вас есть два идеала, то ну как бы умножаете на любое целое число, вы можете норму сдвинуть. Да?
Ну да, не, ну
умножая образующий.
Это понятно.
Да. Поэтому.
Okay.
Yeah, so we will find B, beta, as such that A times B is equal to psi, some element psi, where psi will be integer. So we shall precisely find the ideal, which is complementary, which will give you integer number. And actually, notice that, yeah, so just the claim is that just yeah, so this yeah, so in order to do it, yes, this will be sufficient to do the following. So note that do it to find B. So beta. It is just sufficient to find psi with psi inside A. So it is sufficient to find psi inside A. Yes, so since we have, since this implies that A times B, so there exists B, yeah, so I shall recall this property explicitly. So in OK, so such that A times B is equal to psi, and this is divisibility property that we have to use that some ideal C is inside A. So this implies that you have decomposition for, if you write down decomposition for C, and the composition for A. So you use the same collection of primes, possibly with different m's which are zero. So you have the following property that C, if you have such inclusion, then you should have inclusion on all powers. Yeah, by the uniqueness. Yeah, so this implies that n i's are bigger or equal than m i's, and b can be taken, put b about p and 1 minus 1, etc. p k m k n k minus m k. Yeah? So yeah, and now we shall use Dirichlet lemma. So I claim that we shall find A, so psi inside A, with some estimate plus estimate on the norm of A, of psi. And we shall do it via Dirichlet principle. So take a box. So take a box. We call it c to the power n. Yeah, so that is just parallelepiped. We have a standard basis. And we shall just bound the coefficients. Yes, so n is just the degree of k over q. And we shall bound, so ai's are integers, so omega is a basis of integer ring, so a ring of integers. And we shall bound coefficients from, so they will be positive and less or equal than the norm. The norm 1 over n. So this is the size of the box, plus 1. Yes, so what we shall have. So we claim that there are, so notice that you have O of k. Yeah, it maps to A of k modulo A. And here we have the box Cn. So we claim that two elements from Cn will map to the same elements, to same residues. Yeah, so two elements in Cn will map to the same the elements with same residues, since the number of elements, so this is a finite set, yeah? So this is finite group. А у нас после, вы не знаете, было занятие, будет у кого-нибудь?
Не знаю.
Ну, просто,
Нас могут увидеть.
да, вот я как бы хочу выяснить это. Просто тут надо прерваться, поэтому в какой-то момент я как не успел договорить. Yeah, so this means that two elements will, and the number of elements in Cn is just the power. Yeah? So a number of elements in Cn. It is just the different coefficients since omega are bases, so all elements are different. So it is the maximum of AIs in the power n, which is, so here is a bad estimate, but, so this is just a norm over n in the power n. Yeah? So which is bigger or equal than the norm of A. And this is finite group of order n Ka. So this means that if so under these assumptions, yes, so the number of elements, yeah, so you see that so in the box there are more elements than in the set we are going to map, so that means that two elements in Cn will map to the same residue. Yeah? So this is precisely Dirichlet principle. And this now we have to use it. Yeah, so we notice that yeah, so if you have this is A and B that belongs to Cn, and they will map to the same. They map to the same class. So this implies that the A minus B is some psi that belongs to A. And now I want to understand what are the coordinates, what are possible coordinates of psi. And if you write down psi, so this is fine observation that psi is so if everything is contained in the box, the difference of two elements, it is they of course I mean the coordinates of the difference of course will be negative, but the size of the box, I mean if we are looking at the box like this, all elements were contained in the box. And if you are looking about differences, it is contained in the box, but the norm of the elements in the box is the same.
Yeah.
Yeah. So the claim is that just AI minus BI are less or equal than maximum of AI BI. So this is less or equal than n of A, 1 over n plus 1. So you have now, let us calculate the norm of psi. So I claim that, if you look at the norm of psi, I claim that it will be also bounded. And we shall write down the estimate. And norm of psi is equal to the norm of, can be calculated via the formula that is obtained by the embeddings. So C1 omega 1. Yeah, so let us denote this by C1, etc. by Cn. And this will be less or equal to than yeah. So where sigma runs through all embeddings of K into Q bar. So the number of embeddings is equal to degree. Yeah? So less or equal than. So this is the number of embeddings. So which is separable degree. Number of embeddings. Inclusions of K into Q bar. Which is equal to n. Then you can, so this is the Euclidean norm, so you bound it by maximum of the coefficients, and a maximum of sigma of omega i's. But this number is just, so this is the universal constant. А у вас занятие?
Что?
Занятие?
Да.
Сейчас я тогда закончу. So this bounds by so this is maximum of times universal constant. So this is n times na modulo 1 over n plus 1. And times the universal constant. Yeah, and this is that's just so this is a product of over all the embeddings. Yeah. So sorry, this is n and the product over all the embeddings. So this is number of elements. So there should be number of elements. Ci and the product over all the embeddings. Ну, давайте я закончу и в следующий раз. Делаем. Да, все, да. Конвертирую. Все, спасибо. Извините.